All right, let's go ahead and continue with our example. So we described it in the last video. We're going to go ahead and perform our procedure now. Okay, so the first thing we need to do is map out our knowns. Okay, so we know that our soda has this mass that was given to us. Our soda starts at a temperature of 20 degrees Celsius. Our ice, I'm going to say T sub I for ice, is at 0 degrees Celsius. And our mass of our ice cubes, there are 3 of them. So my total mass is going to be 3 times, 6, let me write that again, 6.0 grams. Okay, so that would be 18 grams or 0.018 kilograms. It's always good to put things in our SI units. Okay. And again, we're going to be doing something very similar to last time, but now we need to look at the heat when we have our phase change of the ice. Okay, so again, we say that at equilibrium, we will have this be true. My heat of the ice, heat transfer of the ice plus the heat transfer of the soda will equal 0. Okay. So Q of our soda is going to be M of the soda, C of the soda, which it states the heat capacity is going to be the same as water. So I'll put a W there. And then delta T, so my T final minus my initial of the soda, which is 20 degrees Celsius. Okay. Then we have our Q ice. That is going to be the same as this, right? So it's going to be M ice, C of water, and then TF minus our initial, which is 0 degrees Celsius. Okay. But we also have our latent heat that we need to deal with. So that's going to be M sub I times L. We need to know if it's going to be the freezing point or if it's going to be the vaporization point. And we know that it's the freezing or melting point. So it's going to be L sub F. Okay. So then we'll add it together and solve for our T final. Okay, whoops, sorry about that. So I'm going to go ahead and let me actually do at least one more step here. So let's add these two together. We'll have MSCW times T final minus 20 degrees plus M sub I CW, and this is just going to be T final since that's 0 degrees, plus MI times LF equals 0. Now from here we can solve for our T final, and that'll be MSCW times 20 degrees minus MILF, and that's going to be divided by MSCW plus MICW. Okay, so we need to plug everything in. Let me go ahead and note that LF is 334,000 joules per kilogram. Okay. And this is from the equation in, or I'm sorry, the table in your textbook. Okay. So once we plug all of our values in, let me also note W, 186 joules per kilogram degrees Celsius. Okay, we find that our final temperature is 13.3 degrees Celsius. Okay? All right, so remember when you're doing these problems that we have this hidden heat, okay, called latent heat, and that's going to be when we have the phase transition, phase change, okay? So watch out for that when you're going through these problems, okay? Okay, so let me also talk about something called sublimation, and that's going to be the transition from solid to vapor. Okay, an example of this would be dry ice, which is, we've probably seen it, maybe not, but that's when the solid carbon dioxide turns into a fog, you can say, okay, or some kind of vapor. So a lot of times we see this at parties or something. We have dry ice and we put it into a bowl of punch or something. Maybe the kids love that, and then you can see this like fog stuff come out. Okay, so this is called sublimation, and it occurs because the equilibrium vapor pressure of solids is not zero. Okay, and the energy required to change 1 kilogram of a substance from solid to vapor is going to be Q equals M times L sub S. Okay, so this is now going to be the sublimation latent coefficient here. Okay. Now let's talk about heat transfer methods. Okay, there are 3 main types. Hopefully you've heard at least of one of these. The 3 of them are called conduction, convection, and radiation. Okay. Conduction is going to be through physical contact. Okay, so you touching a desk that's cool, or anything like that. So conduction, physical contact. Convection is going to be by a macroscopic movement of a fluid. Okay, we see convection a lot when we're boiling water. Okay, we get this motion of fluid. Okay. Then we have radiation, and that occurs when there are electromagnetic waves involved. Okay, and that's when these are emitted or absorbed. Okay, so we've got something like microwaves or infrared radiation, visible light, any other form like that being emitted or absorbed. So here in a house, okay, say like this building or this house, we have all 3 of these going on. Okay, so say we have these windows that are open, or actually they don't have to be open, but this is cool air that's coming in, okay, and goes to the heat, because cool air will sink while hot air rises. Okay, and we'll talk about that in a minute here, more in depth. So we've got some kind of convection, kind of motion of fluid, right? Gas is a fluid. We also have conduction. So if we've got this fireplace here, okay, it's heating the floor by touch, right? It's touching the floor there. Then we also have radiation, and that's going to be from the flames. Okay, this is going to give off visible light radiation, okay, and it's going to heat the surroundings. Okay, so let's talk about each of these in a little more depth. Okay, the first one is going to be conduction, and this is going to be conduction of thermal energy of a material. Okay, it depends on the cross-sectional area of the material that's being in contact with each other and the thickness of the material. Okay, so let's look at this here, this figure. Okay, we have 2 different substances coming into contact at this surface. Okay, so this will then create some kind of surface area where they're touching. Okay, we have this side, we'll say side 1 is the higher temperature, and this side 2 is the lower temperature. Okay, the higher temperature energies are going to start to come into contact at that surface and try to transfer their energy over, right? Remember that heat will go to the go from the hot to the cold. Okay, so that's the same thing that we have here. We have this hot stuff trying to get into the cold area. Okay, and we've got this is showing the energies before and after they collide with this surface. So on this first side, we have a higher energy because it has a higher temperature. Okay, so these energies are higher, and then once it comes to that surface, it loses energy to the other side. Okay, so the one with lower energy then is gaining energy and therefore gaining temperature. Okay, so it's getting hotter on that side. Okay, so we want to know then what this transfer rate is between these heats. Okay, these two different objects, two different substances. And that's going to depend on the material properties described by this coefficient of thermal conductivity, and that is K. Okay, so now let's look at this here. This is going to be a little easier to understand here, maybe. Okay, so if we have two substances coming into some contact, okay, we have that this area over here is T2. The temperature is higher than T1. So this is hot, this is cold. Okay, and then they're coming into contact with each other at some area. Okay, so whichever the higher temperature is, so T2 in this case, will have the thermal conductivity K. Okay, so the rate of conductive heat transfer through a slab of material is described by this equation. So Q over T, that's the rate of the heat transfer, is equal to this thermal conductivity coefficient times the area where they're touching, okay, times T2 minus T1, so the hotter temperature minus the colder temperature, divided by the distance at which, the thickness of the material. Okay? Okay, so this is what we are going to be looking at when looking at conduction. And this rate will be in either joules per second, which is watts, or kilocalories per second. Okay. A will be in meters squared and D will be in meters. Okay, so let's go ahead and do an example of this, which again, I'm not going to be able to finish in this amount of time, but I will finish it in the next video. So example 14.5. This states a styrofoam icebox has a total area of 0.95 meters squared and walls with an average thickness of 2.5 centimeters. The box contains ice, water, and canned beverages, all at 0 degrees Celsius. The inside of the box is kept cold by melting ice. How much ice melts in one day if the ice box is kept in the trunk of a car at 35 degrees Celsius? Okay, so we'll look at this in our next video.